finish the syllabus, and it is only March 22nd. Probably we are getting the time, isn't it?
But not even one class.
Because that is the problem, because it is already end of January. So 2 months we have, not 2 months. And we have to conduct 3 quiz on the 3 module, 5 quiz on the 5 module. Plus we have to finish the syllabus. So it is tough to manage the time. I think you will understand that.
Okay, sir.
Okay, if you have particular problem, you may ask, then I'll answer it. Otherwise, please read. If there is any question arises, you may contact with me through team or email or phone. Any you can just mail me, send me a mail, I will give you the answer. Okay?
Sir, please provide this PPT.
No, I have already provided the notes. I have already provided the departmental notes. You read that one. Okay?
Okay, sir. Okay.
Okay. So we are going forward to the next module. As I have already mentioned that we have very short time to finish this syllabus. So we are going to the next module. Next module is on your covalent bonding. As we have discussed in the very first class about the 4 types of bonds, among those we have already discussed the 3 types. The next we will discuss about the covalent bond and organic compounds. Covalent bond mainly present in organic compounds. Okay, here is the syllabus about your second module, covalent bond. I think you have idea about the Lewis electron dot structure. Still, we will give some introduction about that. Valence bond theory, molecular orbital theory, molecular orbital of diatomic, polyatomic system, including hybridization, conjugation, Huckel molecular orbital theory of conjugated system, Huckel molecular isomerization, geometrical isomer, optical isomer, chirality, antisyn, cis-trans antisyn isomerization, Wake, Fisher, Newman, Sawhorst projection formula, interconversion of EZ-DL-RS nomenclature system, conformational study of ethane N-butane cyclohexane, okay, etc. So this is about your syllabus, and we will start discussion from the covalent bonding, from the definition that covalent, as we have defined, it is the lone pair sharing by both the bonded atoms. Okay, example of compounds having covalent bonds include the gaseous atoms like O2, N2, H2O. As in the very first class we have already discussed that what is the classification of bonding. This is one type of bond, and organic compound like CH4, and most of those organic compounds is having the covalent bonds. That is, electron is equally shared by the 2 atoms to form a bond. Okay, here I think you are already aware about the Lewis electron dot structure. For as we know that boron, carbon, nitrogen, oxygen, fluorine is having this number of electron. Boron is 3, sp2 2p1, 2s2 2p1, This is the valence shell electron, not the whole configuration we are discussing. And carbon is 4 valence shell electron, 2s2, 2p2. Nitrogen is 5, 2p3. Oxygen 6 and fluorine 7. Here, in case of simple covalent bond formation between the hydrogen, to draw the Lewis dot structure, we are giving the valence electron around hydrogen. Valence electron is 1. So from each we can put the dot inside so that to mean the sharing, or we can draw just a bond in between them to express the 2 electron present here. Okay, in case of fluorine, here is the 7 valence shell. So you can see the we have drawn 7 dot electron around the fluoride to show the Lewis dot structure of F2. Okay, or we can draw like this. In case of nitrogen, here is the drawing. So here, in case of CO2, here is the drawing. So here, F2, as per Lewis dot structure, F2, the pair of electrons shared is the bonding pair. The electron pair shared is the bond pair, okay, or bonding pair. And the electron without sharing, those are known as lone electron or lone pairs. Okay, and they are also called non-bonding electrons. Those are not interacting with the other fluorine atom. In carbon dioxide, in case of carbon dioxide, carbon is not having any bond lone pairs, but oxygen is having 2 lone pairs on it, with carbon is having the 4 bond pairs and oxygen is having 2 bond pairs. Okay. So, and in case of nitrogen, nitrogen shares the 3 bond pair, so it is the triple bond. If 2 bond pair is there, then we can say it is double bond. Okay, and here you are aware about the octet rule, that each atom should have the 8 number of electrons in their valence shell. Is the stable structures. The tendency of molecules or polyatomic ions to have structure in which 8 electrons surrounded each atom is known as octet rule. In case of H2O, the oxygen is having 6 electrons around its in valence shell. So it is sharing with 2 hydrogen to have the 8 electrons on the oxygen. Whereas in case of hydrogen, it is not possible to have the 8 electrons. It will get 2 nearby inert helium structure. So 2 electrons. And in case of fluorine, the same, having 7 electrons, so it will share only 1 electrons to have the full octet. Here, in case of charge on it, the formal charge equal to number of valence electron minus number of lone pair electrons plus number of bonding electrons by 2. Okay, this is the formal charge, if any, that we may calculate number of valence electron minus number of lone pair electrons plus number of bonding electrons by 2 within a bracket. So in case of, you can calculate this in case of, say, ammonia. In case of ammonia, we know number of valence electron on nitrogen is, number of valence electron is 5 minus number of lone pair is, in case of nitrogen, if we draw the Lewis dot structure, in case of ammonia, if we draw the Lewis dot structure, it is 1 number of lone pair electrons. So 1 plus number of bonding electrons is 1, 2, 3, 4, 6. 6 by 2. So 3. Okay. 3 plus 1, 4, and this is 5. sorry, number of lone pair electrons. So 2, you have to write here 2, not the 1. Number of lone pair electrons. So 2 plus 3, 5, and number of valence electron is 5. So here is no net charge. In case of ammonium ion, if you calculate, you will see that, or amide ion, if you calculate, you see that here is formal charge plus or minus. For this, the lone pair number of valence electron is again 5, and number of lone pair electrons is 0, and number of bonding electrons is 1, 2, 3, 4, 5, 6, 7, 8. 8 by 2, so 4. So 5 minus 1, minus 4, so 1. So formal charge on nitrogen is plus 1. Is it clear? So this way you can calculate the charge on the ions. In case of calculus structure, this is just the extension of the Lewis-Dawes structure. Here in calculus structure, we are not showing the lone pairs. Only we are showing the covalent bonds. Like in water, we are showing the bond with hydrogen. OH bond formed, 2 OH bond is formed. In case of ammonia, 3 hydrogen is bonded with nitrogen. So we are not showing the lone pair on the atoms. This is simple Lewis-Dawes structure converted to calculus structure without showing the lone pairs on the atom. No need to think about the valence electron present. But here the problem is exception of the octet rule. Probably you are aware about that. In case of compound like boron trifluoride, in case of boron, the octet is not filled. In case of boric acid also this is true. When here coordinate covalent bond is formed, when salt is formed between NH3 and NBF3, the nitrogen is donating to B to form the coordinate covalent bond, because B is having less octet. So it is acting as a Lewis acid, and NH3 is having lone pair. It is acting as a Lewis base to give the salt. Similarly, here the also exception you can see in those compounds where more than octet means more than 8 electron is present, or less than 8 electron is present in case of boron. Okay. Now, in case of the covalent compound, say for hydrogen, HH bond is formed. In case of hydrogen, the bond polarity is 0, or here is no bond polarity. Bond polarity arises due to electronegativity distance between the two centers or two atoms. Here both the hydrogen center, so the electron is equally, means 50-50 sharing by both the centers. But if we think about HCl, in that case, chlorine atom is having more electronegativity than the hydrogen. So the sharing pair is not equally shared by these two. Rather, due to more electronegativity on chlorine atom, it is little bit shifted towards the chlorine. Means chlorine sharing more. Chlorine is having more attraction on the sharing pair rather than hydrogen. That is why hydrogen is having having delta positive charge and chlorine is having delta negative charge on it. That is known as bond polarity. It is arises for the covalent bond when the two center or two atom is not is having the electronegativity difference. In that case, the sharing pair is not exactly equally shared by the two centers. Rather, one atom attracts more, and that is why it is having delta negative charge, while other is having delta positive charge. The meaning is that little ionic character introduced into the covalent bond, and that is why we will have the bond polarity. And here,
सर एक्सेप्शन वाला पार्ट एक बार फिर से
sorry,
एक्सेप्शन वाला पार्ट सर एक बार फिर से बताइए.
in case of exception of the octet rule, here boron is having sp2 2p1, 3 electrons on the valence shell, and in bf3, in case of bf3, boron is having 3 electron, valence electron, and it is bonded with 3f. So around boron, how many electron is present? Around boron, only 6 electron is present. But it should have the 8 as per the octet rule. Is it clear?
Yes, sir. Yes,
So
sir.
it is the exception, and that is why it is behaving as a strong Lewis acid. Okay, to accept the lone pair from nitrogen to form the ammonia, this salt. Okay, in case of other compound, if you see this is SiF5 minus, here you can see number of electron is more than the octet, or 8. Here you can see the 5 fluorine atom is bonded with the silicon. So 10 number of electron is present. Is it clear?
Yes, sir. Yes, sir. Okay.
And that is why it should be 8, but it is 10. So more than octet number of electron or less than octet number of electron may be present. But those are the exception, very few compounds having those. Is it clear?
Yes, sir. Yes, sir.
Okay. So what we are discussing about the bond polarity, and as bond polarity arises means one center is delta positive charge and other center is delta negative charge. So here one dipole moment, we are explaining one term, that is dipole moment. Dipole moment is the vector property. It is having a particular direction from the positive center to towards the negative center. Okay, and the dipole moment depends on the polarity. We are calculating the dipole moment mu equal to QR. Q is the charge developed on the center. See, the same amount of positive and negative charge will generate into the R distance between them, and unit is dBi, or D is used. Okay, and if mu is 0 in case of no charge like hydrogen, mu is 0, so molecule is said to be polar. And as the value of mu is increasing, means charge separation or distance is increasing, in that case the polarity will increase. And remember that it should have a particular direction. Like in case of HCHO for this molecule. Here the direction we have to add like a vector. The total having the bond polarity and individual bond dipole moment is giving a net dipole moment. Net dipole moment for the molecule, which is a vector addition. Not only we can add the value to get it. No, we should add it like a vector. Okay. In case of CO2, here you can see the individual CO is having the bond polarity, but net dipole moment for the molecule is 0. This is because CO2 is linear compound, and as one CO is having the vector just opposite to the other CO with same value, and that is why one is cancelling the other, having net dipole is 0. If we consider the CH2Cl2, you may expect that it should not have any dipole because of this type of structure. But this is not the true. CH2Cl2 having the net dipole moment. This is because the structure is not exactly the planar. It is the tetrahedral compound. In case of tetrahedral compound, the vector is not just opposite. And that is why here is a net dipole moment. Rather, it is having strong net dipole moment. It is not 0. Let us explain about the bond polarity little more. Say for hydrogen, it is non-polar, having the bond polarity 0. In case of HCl, HC, here electronegativity difference is very small, and that is why those are slightly polar. If we increase little polar difference of electronegativity in case of HCl, the polarity is further increased. In case of CLI, it is very highly polar, but little covalent. And when we are going to NaCl, it is 100% or almost polar. This is forming a ionic compound. So as the difference of electronegativity is increasing, the polarity is increasing, and in case of ionic compound, due to having high electronegativity difference, the electron is transferred from one atom to other to give the ionic bond. So in case of covalent compound, here is a little ionic character if the two adjacent atom is is having electronegativity difference. Even the molecule may have the dipole moment. Is it clear?
So the examples which you gave.
Sorry? Sorry?
So the examples which you gave above, we have not discussed them.
कौन सा एग्जाम्पल? ये वाला?
सर ऊपर वाला?
ये वाला ना?
नहीं सर, इसके नीचे.
हाँ.
वो
तो डिस्कस किया ना.
अच्छा सर, वो आप इतना तेज पेज ये किए ना कि हमको इल्यूजन वर्क याद नहीं किया. सर आप ऊपर नीचे किए ना, उसमें हमको लगा कि आपका छूट गया एक डायग्राम.
नहीं छूटा नहीं. देखिए इधर बहुत सारा एग्जाम्पल है, हम सिर्फ एक एग्जाम्पल ही डिस्कस किया है ना. सेम एग्जाम्पल है, आप कैलकुलेट करके इसको निकाल सकते हैं. ठीक है ना?
हाँ सर, हाँ सर.
है ना. और इसमें भी तो हम कंसीडर किए ना, ये भी तो एक्सप्लेन किया है ना.
हाँ सर.
So here is the limitations of Lewis structure. The limitations is that some of the compound is having more or less number of electron. That is, octet rule is not fully valid to draw the Lewis structure. Second is that geometry of the compound is not explained in Lewis structure. Like in case of CH2Cl2, as per Lewis structure, we can draw some of the properties also. Am I audible?
Yes,
Yes sir, you are. For few seconds you were.
Okay, no problem. So for some of the property like dipole moment, solubility, which depends on the geometry, that is not clearly explained from the Lewis structure. So that is why we are going to the next concept in order to explain the geometry. This is known as Vsapr theory, valence shell electron pair repulsion. Vsapr theory. Okay. Here, first we read the assumptions, then we will discuss with example. Here, the geometry of a molecule depends upon the total number of valence shell electron pair and the central and around the central atom in a molecule. Okay. So geometry depends on the valence electron present. That is bonded pair or non-bonded pair on the central atom. We must have to consider one atom as a central atom. The repulsion between valence shell electron pair determine the shape. In order to minimize the repulsion, electron-electron repulsion, or to acquire a minimum state of energy, when the repulsion is less, the energy is minimum or stabilize the molecule. So in order to gain the maximum stability, the valence shell electron pair keep as far as possible. Okay, within the structure, those should be placed as far as possible. In case of more than one geometrical arrangement, if possible, the arrangement should be depend on their repulsion, bonded or non-bonded electron. In that case, the lone pair repulsion is greater than lone pair, then bond pair, because bond pair is sharing with the other center. So this here the repulsion is decreased. In case of lone pair, it is solely present on that atom. That is why the repulsion is more. And for two lone pair, the repulsion is highest. For one lone pair with bond pair, the repulsion is little less. And for bond pair, it is minimum. And repulsion between the electron pairs at vertical greater than 115 apart can be neglected. So if the angle is more than 115, in that case, no repulsion we may consider. Okay. above 115 degree angle, here is repulsion is 0. And by considering the Vsapr theory, we can explain the structure. Okay, so if we consider the geometry of the atom having the two bond pair, so two bond pair must be at the 180 degree distance, highest possible distance. This is the linear geometry for AX2 type of compound like BeF2. Is it clear? It is trigonal planar, 120 degree angle to place the bond pair into the highest distance, like BF3 has this type of structure. In case of AX4, CF4, the angle becomes 109 degree in tetrahedral structure. For 5, AX5 or PF5, it is trigonal bipyramidal. And in the trigon means the triangle in the plane having 120 degree angle and 90 degree angle for above and below. And for octahedral structure, it is SF6, A6 compound. So here is the examples. In case of regular structure, when in case of compound having the lone pair, the regular structure may be distorted. Like in case of CH4, the 4 bond pair is present, no lone pair is present, so it is the methane tetrahedral. But if we consider the ammonia, ammonia is having 1 lone pair and 3 bond pairs. So lone pair, due to higher lone pair bond pair repulsion, it is although should have tetrahedral structure, but it is near to trigonal pyramidal structure. Means angle between the lone pair and bond pair is increasing, whereas bond pair angle is little decreased to have a trigonal pyramidal structure. Similarly, in case of water, 2 lone pair is present and it have a bent structure of 104 degree 5 minutes because 2 bond pair repulsion is higher. Here in case of ammonia, you can see only 1 repulsion of 1 bond pair. That is why reduction of bond pair 1 lone pair, and that is why repulsion of bond pair angle is less. For 109 degree, it is only 2 degree reduction. Whereas in case of water, 2 lone pair repulsion, so bond pair angle is further reduced to 104. Is it clear?
Yes, sir.
Yes, sir.
Okay. So depending on the number of explain the geometry from the Vsapr theory. It may distorted from the regular geometry is lone pair instead of a bond pair. Similarly, PF6 is trigonal bipyramidal, but when we are coming to SF4 having 1 lone pair instead of a bond pair, in that case it attains a distorted trigonal bipyramidal structure. Okay, and when we are coming to this, it forms a T-shaped compound because of interaction between two lone pairs. And XEF2, 2 bond pair, 3 lone pair. So it actually attains the linear structure, almost linear structure. Is it clear? And similarly, it is shown for octahedral SF6, square planar BRF5, and square planar ACF4, square planar pyramidal. When one lone pair is present, and attain the square planar structure when two lone pair is present. So by this way, you can explain the structure using Vsapr theory. Here, polarity, molecular polarity, we can explain by using the Vsapr theory. Okay, like in case of CO2 on the carbon, there is no lone pair. It is bonded with 2 oxygen. So it is linear. As it is linear, so polarity is cancelled by the opposite direction with having same value. So it should be non-polar in nature, which we can explain for Vsapr theory. Because of oxygen having larger electronegativity, in case of H2O, if we consider the H2O, here is a angle is present, and oxygen is having the more electronegativity than hydrogen. So actually addition occurs for CH bond, so having a particular polarity of 1.85 delta. Okay. Similarly, in case of BF3, this is what should be the case for BF3, whether it is polar or non-polar?
Trigonal planar, sir.
BF3 का क्या होगा? पोलरिटी रहेगा कि नहीं रहेगा?
नहीं रहेगा,
नहीं रहेगा,
जीरो नहीं रहेगा।
non-polar.
Okay, I think you know that one, that in case of BF3, the addition of 2 BF bond is just opposite of the other one. That is why it is, as it is trigonal planar. So it is not having any dipole moment. Is it clear? So
Yes, sir.
I think you may, in case of NH3 having the dipole moment, so here is given little examples. Molecule like carbon tetrachloride, methane are non-polar. This is due to the same reason. So here is a little for CO2, H2O, H2S, SO2 is having dipole moment because SO2 structure is not same like CO2. Okay, it is having lone pair on sulfur. That is why different structure. NH3 is trigonal pyramidal and NF3. So here question is why NH3 is more polar than NF3. That you have to answer and explain the trend of, say, CH2Cl is having 1.92. Only 1 chlorine is present. Still the polarity is high. When 2 chlorine is coming, polarity decreases. When 3 chlorine is coming, the polarity less. And in case of 4, it is happening. that you have to explain. And in case of NF3, NH3 why more polar than NF3, that you have to explain in the
Sir, in
yes please.
Sir, in NH3, in case of NH3, all dipole moments are adding. N भी जो है वो H से खींच रहा है और lone pair is also in the same direction, तो add होगा और NF3 में आपका फ्लोरीन वाला cancel होगा. फ्लोरीन वाला खींचेगा और cancel out होगा.
No, I think you have missed the answer. In case of NF3 and NH3, whatever be the compound, the geometry is same, and as geometry
is same, but direction
no direction. In case of NH3, please read more about.
एक चाहिए ना कोई.
Please read more about that. You will find the answer. Okay. आप जो आंसर बोल रहे हैं सही नहीं है. Anyway, please find it. We will discuss in next class. So here is the limitations of Vsapr theory. What are the limitations? It fails for isoelectronic species. Isoelectronic species means having the same number of electrons around the center.
नहीं ये हटा दे. वैसे नहीं हम घुमा दे पे जगह है.
नहीं गलत कुछ नहीं, इसको हटा दो.
Okay, so here are the limitations. According to Vsapr theory, shape of the molecule we can determine depending on the bond pair and lone pair repulsion. However, for two isoelectronic species can differ in geometry despite the fact that they have same number of valence electrons. For example, IF7 and TF7 have 56 electrons, and Vsapr theory predict both to be pentagonal bipyramidal. However, electron difference and X-ray diffraction data indicate that equatorial F bond of TF6 are not coplanar. Moreover, the bond length of IF and TF bonds different. So in case of isoelectronic system, here is the little difference in structure that is not considered or that cannot be explained from Vsapr theory. Here is the example considering IF7 and TEF7 minus. Okay. So TF7 correct shape is not explained, although it is isoelectronic with IF7. Okay. Also fails to predict the structure of certain compound because it does not taking the account of relative size of the substituents. That is stereochemical inactive lone pairs into account. Okay, so Vsapr model also fails to predict the structure of certain compounds because it is not taking the relative size of the substituents. Say in case of fluorine, bromine and iodine, the iodine size is higher than the fluorine. So repulsion for iodine is more. That we have to consider. Like, and some of the pair is...
So can you explain it once again?
Say in case of fluorine, bromine and iodine, fluorine is having smaller size and iodine is having bigger size. So iodine may have higher interaction or higher repulsion, but it depends on also the bond distance. Like CF bond distance is smaller than CI bond distance. So as bond distance is increasing, repulsion is decreasing. And as size is increasing, for iodine size is higher, so repulsion is more. But as bond distance is increasing, it is compensating with the repulsion of the big size. That is why we must have to, in summary, we must have to consider that in the VS pair theory, which is not explained in VS pair theory. And also, in case of valence s electrons, here inert pair effect, you may find about that inert pair effect. The s electron remain inert and it remain as a non-bonded. In some of the compound, but for from VS pair theory, it is not possible to give the accurate geometry for those transition metals like ACCl6, TeCl6, ACCl6 2 minus, TeCl6 2 minus, BrF6 minus are predicted to adopt pentagonal bipyramidal geometry as per VS pair theory, but it is having the different structure. Okay, here is TeCl6 2 minus. As per VS pair theory, it is having this structure. As per VS pair theory, it should have the tetragonal bipyramidal structure, but it is having octahedral structure. Because s electron remain the inert. And isoelectronic, here having the 7 1 lone pair, so it is having this pentagonal bipyramidal structure. Pentagonal pyramidal structure because of lone pair we are not considering. So you try to solve those problems. Predict the shape of silicon tetrachloride. Using VS pair theory, you can try to solve those problems. What are the shapes of H3O minus and ClF2 minus? What is the shape of ICl4 minus? CO2 is linear, but NO2 is bent. Explain. What are the shapes of NO3 minus and XCOF4? Okay, using VS pair theory, you can try to solve those problems. Okay, so I think we can leave here, and next class we'll discuss about the valence bond theory to overcome the limitations of the valence shell electron pair repulsion theory. Okay. And next Monday we are going to take your quiz. So please be prepared for that. Quiz from the first module. And Monday, no need to join in the class. The question paper will appear in the post section. You click on that and attend the quiz. Okay, no need to join in the class. Is it clear?
Yes, sir.